this video, we're going to use the definition of a derivative to determine the derivative of this cubic function. Now, if you're well into your calculus course, we are not about to do this problem the easiest way. You know the power rule, you know shortcuts to taking derivatives that have been proven to work with this definition, but early in your derivatives unit in calculus, whether you're in AP Calculus in high school or Calculus 1 in college, you'll use this definition for a week or two to try to find derivatives. So let's go ahead and show how this applies to this cubic function. So here's the definition of the derivative, and what we need to do is we need to build this limit. Now, most of the work associated with this problem is going to be involved with f of x plus h. So here's my function f of x, and if I'm trying to compute f of x plus h, what I'm going to want to do is I'm going to want to replace this x and this x with just parentheses, and within those sets of parentheses I want to place x plus h. Now this top line right here definitely has quite a bit of algebra that can be done with it. There's not really any calculus happening down through this stretch of the screen. There's no limit involved. It's just simplifying f of x plus h. So you can't distribute an exponent, but what you can do is you can write out x plus h cubed as repeated multiplication. You can distribute this 2 into that set of parentheses, so I've done that. And now I need to start expanding this. So I'm going to take the first two sets of parentheses and multiply them together. So I'm going to FOIL them out. First times first gives me x squared. The outer multiplication and the inner multiplication both give me xh. So I have two xh's. And then last times last is going to give me h squared. Now I still have to multiply by this final set of parentheses containing x plus h. And that's what I'm going to do as I transition from this line to this line. Now these pieces here just had to copy into that line. Didn't really do anything with them. They just had to kind of go along for the ride for a couple of lines. And now I need to multiply this 3-term set of parentheses with this 2-term set of parentheses. That's going to be 6 total multiplications. I need to do the first item here times the first item here, which gives me x cubed. I need to do the first item here with the last item here, which gives me x squared h. The middle item times the first item is going to give me 2x squared h. The middle item times the last item is going to give me 2xh squared. The last item times the first item is going to give me h squared x. You'll notice I did not write that as h squared x. One of the things I see students have a little bit of trouble with from time to time when using this definition is if they write this term over here, I guess I'm trying to go to this one. If they write this term here as an xh squared term, and then they write this one as an h squared x term, they might not think those are like terms. But the order of multiplication doesn't matter. So I would say if you've listed x first in some of these other multiplications, I would continue to list x first in any of the remaining multiplications, even if technically you're looking at it and seeing the h times the x on your page. And then the last item times the last item gives us h cubed. And again, these 3 pieces at the end, they're just copying in. I do have some like terms here. I believe this and this are like terms, right? They have matching variables and exponents. So I have 1 of them here, 2 of them there. So I have 3 of those total. And then this and this term would be like terms as well. I've got 2 xh squareds here, and then I've got 1 more xh squared in that spot. So I've got 3 of those as well. Nothing combined with the x cubed, nothing combined with the h cubed, and again, these 3 pieces at the end are just hanging out, continuing to be at the end of that line every time. All of the work that we've discussed so far has been to figure out what goes in this spot within our definition. So I'm taking this answer and I'm placing it prior to the subtraction in our limit definition of the derivative. So I've got that answer written out across this line here. Then I've got my subtraction, and what I need to subtract off is f of x. So I'm subtracting off exactly what I had on this top line. Now I put this set of parentheses here in blue because this is something else that I oftentimes see students make mistakes with. Unfortunately, if you leave this set of parentheses off, there's not really a way back. You're going to need some cancellation to occur, and if it doesn't occur properly, and if the parentheses aren't there, it won't, you're not really going to be able to get out of the weeds. So this f of x the whole thing needs to be subtracted off, which is why I have the parentheses here. I'm not just subtracting off the first piece of f of x and then copying in the rest. I'm subtracting off the quantity that represents f of x. Now, why is that important? Well, if you look at the x cubed that's here, distribute this negative in to that x cubed, those are going to cancel. We have a plus 2x right here. Distribute this negative into that 2x, and those are going to cancel. We've got a minus 1 here. Distribute this negative into that negative 1, and the negative 1 and the plus 1 after distributing will cancel. So what we're left with is really just 3 pieces. This, 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 and this. So see, I've copied those into my numerator. Now, if I try to evaluate the limit, I'm still going to be looking at 0 over 0, which is an indeterminate form. I need some cancellation to occur with my h's, and what I can do to make that happen, you'll notice all 4 of these terms that are remaining in the numerator possess an h. So if I factor an h out of each of these 4 terms, once there's multiplication as the operation between this h and that bigger quantity, I'm no longer violating the order of operations if I want to cancel this h with this h. So after I do that, I can put 0 in place of the 2 h's that remain. So 0 goes in place of the h that's after that second x. 0 goes in place of the h that's squared. This piece is 0. This piece is 0. What are we left with? We're left with 3x squared plus 2. That is our derivative produced with the definition. If you wanted to use this to find the slope of a tangent line at, say, 5, you could put 5 in place of the x and evaluate, and you have that slope at 5. If this was a position function and you wanted to determine an instantaneous velocity at time 2, you could put 2 in place of the variable here, evaluate, and there you have your instantaneous velocity at time 2. So once you have this derivative, it can do a lot of things. It represents the slope of a tangent line. It determines an instantaneous velocity or an instantaneous rate of change in general. For those of you further into your calculus course, and for those of you watching this video, you will develop shortcuts for this. The job of a derivative is never going to change. It's going to do the things we just referenced, but this procedure for finding a derivative is definitely going to be made much nicer, more efficient. You'll like it more in the coming weeks.